Then we have gamma to the 6, but here we have 4 gammas. So this gives us E squared, E squared, E squared, sine squared alpha over 1/4 squared. So there's a gamma to the 6 there, so we're left with a gamma squared over 6 pi c, right? Over 6 c, and then put in what we've calculated for this. There's parentheses here. We've already taken the b squared, so we're left with a b squared sine squared alpha over the gamma we've taken care of for n. Okay, that's the first result. Now to bring this back to somewhat more convenient units, convenient way to write that, let me first add a c in here. And we have b squared over c squared, that is beta squared, right? So this here is beta squared. Then let's introduce a few other things here. First of all, let's bring in the energy density in the magnetic field. What's the energy density in the magnetic field? In the SARChI units. Energy density in the magnetic field. Remember, energy density in the electric field was epsilon naught E squared, right? The magnetic field was E squared over 2 mu naught, right? That's complete. So maybe we can replace our B squared as 2 mu naught times the energy density in the magnetic field. That'll be the first thing we'll do here. So this brings us to, so just replace this, 2 mu naught squared e to the 4th c, energy density of the magnetic field, gamma squared, beta squared, sine squared alpha, over 3 pi squared. Okay. Now, we do a few more tricks here. Anybody know how the classical electron radius is? Because we're going to replace this now with a characteristic size or cross-section of an electron. Anybody know how you can, the electron is really a point charge. How can you associate a radius or a size to the electron? Anybody know how that's defined? Comes from. So we're trying to figure out what is the classical electron radius, right? Electron. That is, the definition of that is you have the charge Q and see what charge Q actually has as, so if you have one electron, if you had another electron within some radius r, and of course there's a potential energy, right? Potential energy is the product of the two charges over 4 pi epsilon naught times distance, right? That's essentially the potential energy just classically in the static electric field, right? Where that becomes, again, will motivate rest mass energy next week or the week after, where this essentially, this potential self-energy of the electric field equals the electron rest mass energy. That is essentially the definition of the electron radius, the classical electron radius. So, classical electron radius, then here this over E squared over 4 pi epsilon naught C squared. So it's now we see we have E to the 4th here, so we might have some electron radius squares there. Two masses will cancel out, right? So let's take this over here. Or actually, before we do that, now if we know we have this classical electron radius, we can relate this to what we call the Thomson cross-section. So what is the cross-section essentially that this corresponds to? So we call that sigma Thomson. And that will also make much more sense when you actually talk about Thomson scattering, Compton scattering. So essentially the size of the targets that photons are meant to hit to actually interact with the electron, that we can relate to the classical electron radius as h pi over 3 r squared. So in okay, so that means we'll have sigma Thomson as 8 pi over 3, and then we have electron radius squared here, so that is e to the 4th over 16 pi squared epsilon naught squared e squared c to the 4th. That will now use to put in here. Let's see, so we can say, so we have e to the 4th over m squared, that's a factor that we have in there. Let's just plug that in, that is, so here, 6.1. So, gives us 6 pi sigma Thomson c to the 4th over no, that's it. Okay. Squared. But c to the 4th epsilon naught squared is actually 1 over mu naught squared. Okay, now we're almost there. So, T radiated for synchrotron radiation. Let's just plug this in. So we had mu naught squared. So e to the 4th over m squared, we've just figured out here, is 6 pi sigma Thomson over mu naught squared times c, energy density in magnetic fields, gamma squared, beta squared, sine squared alpha, over 3 pi. Okay, that looks nice. That looks much simpler than what we had before, so sorry for all the detours here, but the end result actually makes this very nice. It's just 2c Thomson cross-section. I should start out what this is. So this is called the Thomson cross-section. The characteristic cross-section for all electromagnetic processes for the electron times energy density in the magnetic field, Lorentz vector squared, normalized velocity squared times sine squared alpha. Okay, so this is the energy loss due to synchrotron radiation of an electron that spirals in a magnetic field at some angle alpha. But quite often, we don't really have electrons just with one angle. Typically, we have electrons going in all kinds of directions. What we're often much more interested in is what is this if we average this out over all kind of directions in which we're moving with respect to the magnetic field. So what is it if instead of just for some certain called pitch angle alpha, we integrate this? So if we integrate this overall, alphas, so well that would be like the average divided by 4 pi, integrate overall 4 pi. The integral of 4 pi, of course, can write as 0 to 2 pi phi, and then minus 1 to 1 of alpha, sine alpha, times this, times sine squared alpha, times all the factors that don't connect. Beta squared. Now this, of course, is just 2 pi. And this, well, this is 1 minus cosine squared alpha, right? Gives us it minus 3, gives us 4/3. We've done that, calculated exactly this interval many times. 4/3. So that means the whole factor here is 1 over 4, 4 cancel out, 2, 3, 1 over 6, right? Just gives us 1 over 6. So that means 2 over 6. 8 pi over 3 over 4 pi gives us 2/3. So that means if we just have either randomly oriented magnetic fields or electrons going in all kinds of directions, then we have this as 4/3 c times Thomson cross-section times energy density of the magnetic field times squared. So this is the angle averaged radiated energy. Christian is right now in high energy astrophysics class, where I'm pretty sure this has already come up twice, 3, 4, 5 times. At least it usually does when I used to teach it. So that's a very nice handy formula. That's the energy loss. So you see two important things here. First of all, if we have relativistic electrons, beta, remember is V over C, there's almost 1, so it's essentially just the gamma squared here. That means that the more relativistic, the closer you get to the speed of light, it goes quadratic with the Lorentz factor, that's essentially the energy of the electrons. So high energy electrons radiate much more quickly and cool off much more quickly than low energy electrons. And you'll see that in astrophysics very often, that you have most of the radiation coming from the high energy electrons, but also they lose their energy much faster than anything at lower energies. And it depends on this energy density of the magnetic field. And the nice thing about this result is when we talk, not in this class, but say in the high energy astrophysics class, we talk about scattering, electrons scattering radiation, a process called Compton scattering. Then actually the energy loss of the electrons is exactly the same, only that you replace this with the energy density of the radiation field that you're scattering. actually something very deep, very fundamental in the way that magnetic fields and radiation are essentially the same thing in the quantum physics interpretation. But long story short, this is one result that at least I think you should have seen. You don't necessarily have to remember it now, but if you really do astrophysics, astronomy, and especially if you do radio astronomy, it's almost all synchrotron radiation. So the theory of synchrotron radiation will play a huge role if you do anything in astronomy. That's why I thought it's quite instructive to bring this up now, so now that we have from first principles the tool of how to calculate this radiation. Okay, we still have a little bit of time before coffee break. So any questions here? Any comments? Okay, if not, then, of course, so what this really is the power radiated away. This here, the power radiated away by a particle. That, of course, means, well, we have energy conservation. Where's the energy coming from? Radiation carries energy away. The energy can only come from, if something's radiated away, something has to lose the energy that is going into the radiation, right? Where is it coming from? Well, what sources of energy do we have that we can use up to make radiation? If we have a moving, accelerated particle, then the energy has to come from the particle, right? So that means the particle has to lose the energy that is dumped into radiation. So that's also the real meaning of this. It's essentially the rate at which a relativistic particle loses energy that is going into radiation. Okay, so what we're doing now is actually relate this. So what this energy loss, or the breaking, that just comes from the fact that radiation is reduced, or kinetic energy is converted into radiation. And you can see from the general radiation formula that for relativistic particles that can actually get quite messy. But we can make a simplifying. So if we just say that the velocity is much less than c, so we say approximately, we neglect any velocity terms, then we can actually treat this energy loss in a somewhat coherent way. Then, of course, the radiation and the power going into radiation is just, was it mu naught q squared a squared over 6 pi c, right? Okay, but that is power going into radiation, so that is the same as the power lost by the electron. So what is happening is that the electron is moving and radiating, slowing down because it's losing energy. You can write that as some kind of a force term, right? So let's say the electron is moving in a certain direction. If it's slowing down, that means effectively you have a force term that goes in the opposite direction, that slows it down, right? If you have that, then the power or the energy gained or lost per time, how can you express that in terms of velocity and the force? Very basic classical mechanics. Force acting on a particle with velocity v. Energy lost this. Somebody must remember that. Also faded. right? Gives you the mechanical power from a force, right? So we can write this as essentially minus F dot, because that's the power going in, so this is negative of what the power flow is daily. Okay, so now, in principle, yeah, this doesn't really make it too easy to say what the force actually is, because you have the force now only in the dot product with the velocity, and we have the energy term here. That doesn't necessarily help very much. But what we can say is, if you have some, say, oscillating motion, so where you just go back and forth, and assume that you start out at some t1, and you get back to the same point, in the same state at t2, then we can just integrate over one full cycle here from t1 to t2 minus f dot v t. It's essentially the whole energy, the entire energy dissipated in one cycle. Would be the same as mu naught q squared over 6 pi c minus r. Integral a squared from t1 to t2. And what we can now do is do integrations by part. So we know, because a is dv over dt, right? So a squared is just 2 of that. We can do integration by part, right? So it's minus mu naught q squared over 6 pi c. Then we have a, so that is dt of n, right? And we have one derivative here. To correct, we have to put a dot times v. So plus mu naught q squared over 6 pi c integral from t1 to t2 a dot right? And now at least we have on both sides, we have f here, and we have what we're integrating here, right? Under the same integral. Plus, of course, this we have to take from t1 to t2. Have this boundary term there. But what happens to that if we are essentially in an oscillating motion, that we're getting back to the same point, to the same state? What happens to this term then? T1 and T2 describe essentially the exact same state, just after one cycle. We subtract the same from T2 to T1, right? So this, of course, only if this is really kind of a cyclical motion, then this actually drops off. And then we can dissociate this, essentially, we call it radiation drag sometimes, or radiation reaction. So this thing is called radiation reaction. You can just associate that with mu naught q squared over 6 pi c a dot, but of course a dot you can also write as the third derivative of position, right? Or so it's so it's the third derivative, or the second derivative of the velocity. So the time change of the acceleration gives you some radiation reaction force. So that is be negative, so you actually get essentially a drag. Okay, so the book now makes some kind of weird comment about, well, since we know this is also some kind of just n times of acceleration, you can say that the acceleration scales with its time derivative. What is the solution to something like that? So if we now write, say, some tau as u naught q squared over 6 pi c, then we can write this here as a in tau times a dot, right? What kind of equation is that? What kind of solution would you get on that? Time derivative of a is proportional to a itself modulo some time scale. Right? To figure it out, tau was as the unit of the time. Or a dot is a over tau. What kind of solution do you get from that? Okay. An exponential, right?
Yeah.
And so this gives you a solution that a of t is essentially a naught e to the t over t. And the book then goes on in quite some length in saying that that is something that can't really be, that an acceleration just induces itself and essentially is a runaway process. But what's wrong with that argument? If you remember under what conditions we've actually derived this expression for the radiation reaction time. What kind of motion were we assuming to begin with? We needed to make this turn go away, right? It means we needed to come back to the same point, to the same state, exactly. Because if you actually have some kind of runaway, then you're not in this kind of situation. That means the whole derivation doesn't work. So that the whole argument that the book makes, I really don't understand why he's writing it that just doesn't work. And also, what this means is that it's only valid in the integration, in the average over this whole cycle. This doesn't necessarily have to hold at every time. It's derived as a part in this integral under first dot with the velocity, and this is valid for the integral over the whole cycle. It doesn't necessarily have to hold at any time. So that's why I think the whole discussion in the book about this runaway process and that that's unphysical just doesn't work, just because the derivation doesn't work. Okay, I think we should leave it at this, and I might actually have some time to start talking about relativity. But let's get some coffee.